So this is where we start to talk about chemical formulas and compounds. This is what allows you to do chemical reactions and know what the heck is going on. This is what allows you to not sound like a moron when you talk to people about chemicals. This is what allows you to read a label on a can of soup that has had sodium nitrate added to it. Okay? This is where you start to sound a whole lot smarter, really. And this is functional chemistry. So let's go. All right. So let's just talk in general about what chemical formulas are. Chemical formulas are different depending on whether we're talking about a molecular or an ionic compound. Molecular compounds are doing what with their electrons? Sharing or trading? Yeah, I hear it. Have courage of your convictions. Tell the people at your table. Oh, good. I hear lots of people whispering they're sharing. They know how to share. It's so nice. Everything I needed to know I learned in kindergarten. Always share your electrons, unless you're ionic, and then don't. So for molecular compounds, the formula actually shows the exact number of atoms of each type. It's really convenient because it gives us what's in a molecule. For ionic compounds, okay, are ionic compounds sharing? Heck no! Sharing is so overrated. Sharing's for molecular compounds. One has taken electrons, one has given them up, and so you've got two strongly charged things, two ions that are attracted to one another based on the force of their different electrical charges. They are not sharing. And they're also not physically overlapping their orbitals. They're side by side. In an ionic compound, it's just a ratio. Okay? Ratios are a math concept. Who here has made salt dough? If you play your cards right, we'll probably make salt dough with the kindergarten later this year with some flour. So most salt dough recipes just read 4 parts flour to 1 part salt. Does it matter if you're using cups or pounds or half cups or teaspoons? No. It's just a ratio. Whatever unit of measure you're using, 4 times as much of this as you have of this. That's what an ionic compound shows. So in this compound, KBr, we have potassium and bromine. It's 1 to 1. For every potassium, we have a bromine. In this, CaBr2. For every 1 calcium, we're going to see 2 bromine. It's actually called a bromide ion, but we haven't gotten there yet. So that's the basic breakdown of molecular versus ionic compounds. The first kind of naming we're going to start with is ionic. The ionic, there are 3 sort of subsets of ionic compound naming. We'll do the easiest, then the middle, then we'll complicate it a little bit, and then we'll start into moleculars. So ionic is what we will start with. Okay, you all have a periodic table out, right? You should. Prefix mono means how many? Hold up fingers. 1. Mono, 1. Monocle, unicycle. Wait, no, that doesn't work. Mono means 1. So monoatomic ions are ions that are really, they're easy. They're a single atom that has gained or lost electrons. And you know this from chapter 5, from chapter 6. The main group, which blocks is main group? Can you put your finger on main group? Main group are the S block and the P block. So right now we're just dealing with S and nice. Yeah, I like that. You kind of have to do a split there. We're dealing with the S and P block right now. And they tend to form ions by losing or gaining electrons to look like a noble gas, to have a full upper S and P. So you know that groups 1 and 2 tend to lose electrons. They tend to form what kind of ions? Cations, positive ions. And then 15 through 17. So looking over, starting with boron, aluminum, those tend, oh no, I'm sorry, 15 doesn't gain. 15 still loses. I should change that. 16, wait. No, 15 through 17 do gain. Sorry. 15 starts with nitrogen. That was my problem. And those nitrogen over to 17 do tend to gain electrons, so they form what kind of ions? Anions. Negative ions, because they will have more electrons than they do protons. The D block are the weirdos. We're not going to start to talk about those until later tomorrow. So they do form cations, but it's not as easy to predict. A lot of them can form multiple ions, and you'll get a chart with those. You will not have to memorize them, though honestly, after you've used them for a little while, you'll have the common ones memorized just from using them, which is the best way to memorize things. Okay, I promised you naming. Here's naming. Cations just get named for the element. So, sodium gives up an electron, becomes Na1 plus, and ever so creatively we call it a sodium ion. That was hard. Calcium, same thing, gives up 2 electrons, becomes a calcium ion. So name, compare notes at your table, name for me the ion formed when potassium does that. I heard a few whispers of potassium ion. Woo-hoo-hoo. Not that hard. Not that hard. What about, barium. Barium gives up 2 electrons, becomes Ba2 plus. What do you call it? Tell the people at your table. What do we call it? It's a barium ion! Oh, that was easy. So those are really, really simple. And then, those are the cations. The anions have a slightly different naming convention. Notice that? IDE. So when you form an anion, when you gain electrons, you drop the end of the element name and you replace it with IDE. I'm going to tell you that IDE is pretty stinking important, because right now it's the only ending we have, but by the end of the week we're going to have IDE, ITE, and ATE, and they all mean different things. So you got to keep that IDE straight. Okay, that is very, very important. Chlorine gains an electron, becomes chloride. Sulfur gains 2 electrons, becomes sulfide. So what would we call it when bromine gains an electron? Tell the people at your table. Bromide. Bromide ion. What would we call it when nitrogen gains 3 electrons? Tell the people at your table while I spy on you. Nitrogen gains 3 electrons, becomes, I heard nitride, which is correct, becomes the nitride ion. And in each case, they have that IDE ending that is so important. I don't have a clever mnemonic for remembering that the IDE ion is a monatomic anion. If you think of one, share it with me. You'd be amazed the ones that students have come up with over the years. So if you come up with a really clever way to remember that, please share it. And then you can live in infamy. I'll credit you with it. I'll name it after you. Okay. Easy. Monatomic anions and cations that are main group. If they're positive, if they're a cation, they're just named after the element. If they're negative, they get that IDE ending. For D block, so everybody stick your finger on the D block. That middle ground, that territory where we've got the metals that look like metals. The D blocks, because they form multiple cations, we always have to name them after the charge. So if we have copper that has given up 1 electron, that's a copper 1 ion. What if we have copper that's given up 2 electrons and it is Cu2+? What would you name that? Tell the people at your table. This is a Grant's Tomb kind of question. It's a copper 2 ion. Not real creative, also really pretty darn easy to remember. What if I have, I know, cobalt that has a 3+ charge? What would you call that ion? Tell the people at your table. I hear cobalt 3. Cobalt 3 ion. Okay, good. Good. It's important that we know how to name monoatomic ions, because guess how we start to form the names of the compounds that they're in, using the names of the ions. So it's really important that we name the ions correctly, because that allows us to name the compounds correctly. Okay, so now we get to our first compounds. Prefix bi means how many fingers? 2, bicycle. So, binary ionic compounds are compounds that are made of 2 different elements. And if they're ionic, they're made of 2 different ions. So I'm going to even change that to ions, or ions of 2 different elements, however you want to put it. When we have a binary ionic compound, the positive charges and negative charges have to balance, so that overall the compound is neutral. That's how they are stable. Remember, everything in chemical bonding is about lowering potential energy, increasing stability, making it stable, stable, stable. So when we have magnesium 2+, and it forms a compound with a bromide ion. So we have a magnesium ion and a bromide ion. We have to balance those charges. So we know, just looking at it, that the ratio is going to be 2 to 1. To figure this out quickly, we do what's called crossing over. How many of you remember crossing over from physical science formula writing? Any memory? Doing little crisscrosses? Maybe? Okay. That's the standard answer, is like, I'm not sure we did that. And then by the end of next week, you're like, yeah, we did this. It's just been a while. So to form magnesium bromide, and I'm going to shrink this down. Cut that. We have Mg with a 2+ charge. We have a bromide ion with a 1- charge. A few things about writing ionic compounds. The positive always comes first. So this is just like leading with the good news. The cation ion is always first. So we're going to put Mg, and I'm going to leave a space down here where I will write a subscript. And I'm going to put bromine there with a space where I will write another subscript. The crisscross just refers to the fact that I'm using the magnitude of the charges to figure out how many of each I'm going to need. So I'm going to take the number from this, and I'm going to put it there. And I get a 2. I'm going to take the number from this, and I'm going to put it there, and I'm going to have a 1. So those are my subscripts. Sub means what? Sub means below. Script means to write. These are numbers that are written below. They are subscripts. They are not charges. They do not have a positive or negative sign. They just tell you how many of those ions there are. Now, just like when we did the ABE codes for geometry, if there's only one, we don't have to write the number 1. So when we write the final version of this, we're just going to write MgBr2. So aluminum would need to lose 3 electrons to be like a noble gas. And sure enough, aluminum forms an aluminum ion, which is Al3+. Okay. Look at oxygen. Periodic table out. How many valence electrons does oxygen need to gain to be like a noble gas? Fingers. 2. So sure enough, the oxide ion typically is a 2- charge. These things form a compound, and you've probably seen it. Does anybody have an old aluminum pot at home or an old aluminum storm door? Or have you ever seen an old aluminum storm door? You know, it has little white pits on them. You know what those white pits are? They're a compound formed from aluminum and oxygen. It's the equivalent of rust on aluminum. I used to have an old aluminum pot that I kept around and it got lost in the move. So I'm going to do the same thing. I'm going to write this here with a space for the subscript. Write that there with a space for the subscript. The magnitude, the number of the charge on aluminum, I'm going to bring down here. Oh, the number of the charge there, I'm going to set there. Before you leave here, you need to pick up a practice sheet. The key is online. Tomorrow, in the first period that we're together, we'll look at that, and by the end of the period, you will take a FIP quiz. That's it.